Alright, so this is section 16.4a, Green's theorem. There will be a part B as well. And most likely this will be done in 2 videos just to make sure we get through everything in a timely fashion and the videos aren't too long. Alright, so we're going to talk about this thing called Green's theorem. So far what we've talked about is how to do line integrals, which is the integral over some kind of curve of f dot dr, where f has to be parameterized and dr is the derivative. And we've also talked about the fundamental theorem of line integrals, which can be done as long as we figure out that that f is conservative. And the test for that was that dp dy equaled dq dx as long as we only have 2 variables, and if we had 3 variables, where there was really no easy way to do that as of yet. So we'll get to all that. Green's theorem is a really nice theorem, assuming that you have a couple of conditions met. And we're going to be able to figure out what those conditions are, and then we're going to be able to figure out how to apply Green's theorem to it. So the focus is, if we have the line integral of f dot dr, where f is not conservative and c is closed and positively oriented. Now what does that mean? Whoops. C has to be closed and positively oriented. So if we've got our curve, whatever our curve looks like, maybe it's something like this, but remember that it has to be closed, so we'll end it right there. Within here is your domain inside of here. Now the positively oriented, to be positively oriented, basically what that means is that if you're on C, it has to be done so counterclockwise. So the arrows indicating the direction here are going to go in this direction, counterclockwise all the way around the curve. So if you kind of think of it, the number 2 here says, as you walk standing upright, D is always on your left. So the domain, the domain of this thing has to be on the left-hand side. Again, just think about it as transversing this thing counterclockwise as far as the rotation is concerned. That's probably the easiest way to do it. So if C is a closed simple, which means no holes in it, as you can see up here with D, excuse me, there was no holes inside of this. If in this figure, it's almost looks like it's some kind of, I don't know, maybe a swimming pool, but within the swimming pool then there would be open space with no water or something. That'd be really weird to think about, but that's what it means. So there can be no holes within the inside of it, and the curve is positively oriented, and it encloses a region D. If that's the case, then we can take the line integral over C of p dx plus q dy. That's going to be the same thing as the double integral over D, so the domain up here, of dq dx minus dp dy. Notice those are all partials, dA, so in reference to the area that's enclosed. So one of the questions might simply be, why this? And why not just do that? Well, it's a good question. To be honest with you, if you have a circumstance where you can use Green's theorem, it's going to make things a lot easier than doing the line integral of f dot dr. It's not that you can't do the line integral of f dot dr. Well, maybe you can, maybe you can't. It's going to depend on the problem. But it does make things a lot easier. But here's the thing. These are the same thing. They are the same. So let's show real quickly how that is. So if I take the line integral of PQ and dot that with dx dy, well, I can actually multiply this by dt over dt, because that's just the same thing as 1. So if I were to rewrite that, and by the way, this would give us what's right above there. This can be rewritten as the line integral over c of pq dotted with, now if I distribute the dt on the denominator, let me see if I can highlight that. If I distribute this dt to each one of these in the denominator, just leaving the top dt on the outside, which algebraically we can do, we would get dotted with dx dt, dy dt, dt. And this, of course, would be f, and all of this just represents r prime of t. So really, r prime of t is dr, so this is just f dot dr. It's the same thing. It's just going to be written in a different way. And the last thing we're going to talk about is a little bit of notation on this page before we get to the actual examples. So notationally, if you see this symbol, it's the integral symbol over some kind of a curve, but it's got that little circle around the integral symbol. What that does is it implies that it's a line integral of a closed curve C with positive orientation. So if you see this, that implies that it is a closed curve with a positive orientation. And if you see that, you're able to apply Green's theorem, which is a very, very nice thing to be able to apply. All right, and we restated on the top of the next page here, the notation implies the line integral of a closed curve C with a positive orientation. So example 1 says evaluate the line integral by 2 methods. 1, directly, and then 2, using Green's theorem. And you're going to see that after we do this directly, how tedious it can be and how simple Green's theorem really does make this. So that's kind of the goal of what we're doing on this particular problem. So we're going to evaluate the line integral, first of all, directly. So we've got xy squared dx plus x cubed dy. So first of all, our region C it's got the vertices 0, 0. There we go. 0, 0. 2, 0. We'll call that 2, 0. 2, 3. That's going to be like way up here. And then 0, 3. Whoops. 0, 3. So that's going to create this rectangular box. Here is our region. And since we do have this symbol right here, that indicates that this is going to be a positively oriented, and you can certainly see because it's this rectangular shape, it is closed. So positively oriented just means that we're going in this direction all the way around. So in order for us to actually do this kind of the long way directly, we are going to have to define all of these sides. So we'll have, it doesn't really matter where you start in this case, we'll call that C1, we'll call that C2, we'll call that C3, and we'll call this one C4. Unfortunately, these are all linear, so because they are all linear, our t values are just going to go from 0 to 1. So now we have to parameterize every single one of these lines. So let's go ahead and just start off with C1. In C1, x goes from the point 0, 0. Let me write those in there just to make sure they're there. Oops, forgot that over there. And then this would be 0, 3. So the points go from 0, 0 to 2, 0, which means that x starts at 0 and goes up by 2. So x is going to be 2t. And y just doesn't change. Y is always 0. So then when we go to parameterize this thing, we're going to need dx because it's in the original integral. Dx is going to be 2 dt, and y is just going to be 0. Or excuse me, dy is going to be 0. So let's go ahead and look at our integral. Our integral over c1 is going to be, well, let's see, y is 0. So that makes the first part 0, and dy is 0, so that makes the second part 0. That's really nice. The first integral is literally just 0. Okay, let's look at C2. Might have to do a little bit of scrolling back up and down here on this for you guys. You should have enough paper on yours to be able to complete these. So C2. So C2 is the one on the right there, so that looks like it goes from 2, 0 to 2, 3. So that means that x, in this case, is always 2. And y goes from 0 to 3, so y is going to be 3t. So dx is 0, and dy is 3 dt. So again, kind of looking back at the original integral here, I know that since x is 2 and y is 3t, but dx is 0, we're going to start off with 0, because the dx part looks like we're actually going to have something here for the dy part. So we're going to get plus, let's see, x cubed, well, that's 2 cubed, so that's going to be 8. dy, which is times 3 dt. So I actually do have a little bit of an integral to do here. So we're going to end up with the integral from 0 to 1 of 24 dt, which of course is just going to be the antiderivative, 24t from 0 to 1, which is just 24. So far, we've done 2 of them. We've gotten 0, we've gotten 24. Let's go ahead and take a look at C3. So C3 is going to go from 2, 3 to 0, 3. Now make sure, because direction is important here. It's going to go from 2, 3 to 0, 3. So let's see how that changes anything if it does. Let's go in red there. So C3, x is going from 2 to 0, so it's actually going down. So that means that our x is going to be negative 2t, and y was just constantly 3, it doesn't change. So again, our dy is going to be 0, our dx is going to be negative 2 dt. So going back to the integral, we have xy squared dx, xy squared dx. That's actually going to give us something there. So we'll have the integral from 0 to 1 of xy squared. So y squared is 9 times x is going to be negative 18t dx. So it's times another 2, negative 2 dt. And then the last one was x cubed dy, but dy is 0, so we're done with that part right there. So really what we should get here is something doesn't look right. I'm going to get a 36t out of it. How did I make a mistake there? Oh, I know what I did. Okay, I got to go back for a second here. I apologize. Let's fix this mistake. Hopefully you guys caught the mistake. My x is wrong. Let's change this. So x is incorrect. So x started at 2, right, and went backwards, so it should be 2 minus 2t, not just minus 2t. So yeah, that's the change there. 2 minus 2t, I was going to say, it didn't look right. Now dx, fortunately, is still going to be negative 2 dt. That doesn't change. Y was perfectly fine. So let's go ahead and fix this. It's still going to be an integral from 0 to 1. So let's see. Now we've got, again, it was x, y squared dx. So y squared is 9. So we'll have 2 minus 2t times 9 times dx, which is negative 2 dt. There we go. That looks right. All right, so let's go ahead and work out this integral. So let's see, if we distribute a negative 18 throughout everything there, it's going to be, what, negative 36 plus 36t dt. That looks right. So now we'll have to take the antiderivative, so we get negative 36t plus 18t squared, and we'll evaluate that from 0 to 1. Plugging the 1 in, we'll get negative 36 plus 18, so that's negative 18. Plugging 0 in doesn't give us anything, so we don't have to subtract anything there. So far, we've got 0, 24, and negative 18. Alright, C4, I am going to have to, you know what, let's try a new color. Let's try purple. See how that works. Alright, so let's do C4 down here. So let's check out what C4 is doing. So C4 is starting from 0, 3 to 0, 0. So x is going to be constantly 0, which just makes dx 0. But then y is going from 3 to 0, so I have to make sure I didn't make the same mistake I did last time. Y is going to start at 3, but then go down 3. So dy is going to be negative 3 dt. So when we go to set up our integral for C4, it's going to be an integral from 0 to 1. Now again, the x part itself is 0, so that actually makes, well actually it's perfect, it makes both of these go away. 0 plus 0, because there were x's in both of them. So we get 0 out of that one. Did I do that one right? Let me go back and double check, because I'm not looking at the, so we got x, which is constantly 0. Yes, that's right. Okay, good. Just want to make sure. So, excuse me, in order to figure out the line integral, I have to add up all, oops, sorry about that. In order to figure out the line integral over c, I've got to add up all of the pieces, which is 0 plus 24 minus 18 plus 0. So what we're ultimately going to get out of this thing is 6. Now that was kind of tedious. Took a long time to get through. This is where I'm going to show that Green's theorem is much, much easier. So hopefully you left yourself some space, kind of wrote this the same way I did. And what we're going to show over here is how much easier it is to do Green's theorem. Since it is Green's theorem, let's write it in green, because why not? Green's theorem. Green's theorem states the integral of p dx plus q dy is the same thing as the double integral over d of dq dx minus dp dy dA. Alright, so let's go ahead and set up our double integral. Well, we know that it's going to be over dA, which is an x and a y region. So I'm going to go ahead and set up the dy and the dx. It doesn't really matter if you did dy dx or dx dy. In this particular case, you can do a type 1 or a type 2. Doesn't matter. But since I did y on the inside, let's see, y is going to vary from, looks like from the bottom of 0 up to the top of 3. Your y values go from 0 to 3, and those are functions. They just happen to be linear, so they're constant. And then x, it looks like it varies from 0 to 2. Since we did a type 1, that would have to vary from a number to a number anyway, 0 to 2. And then what we need is we need dq dx and dp dy. Well, let's go ahead and take a look at this and see if we can figure that out. dq dx, now remember q is the second one. This right here is q. And then the one underlined here in red is p. So dq dx, the derivative of q with respect to x, is going to be 3x squared. And then the derivative of p with respect to y is going to be 2xy. And then we can go ahead and take the antiderivative of these things, and we'll see very quickly that this works out to be exactly the same as what we had before. So 0 to 2. Let's see, antiderivative with respect to y is going to give us 3x squared y minus, what is that, xy squared from 0 to 3 dx. Plugging in a 3, we're going to get, now plug in a 3 for y, so we're going to get 9x squared minus 9x. Plugging in 0 will give us nothing, so we're down to this. Taking the antiderivative now with respect to x will give us 3x cubed minus 9 halves x squared from 0 to 2. Plugging in a 2, 2 cubed is 8, so 8 times 3 is 24. Minus, let's see, plugging in a 2 there, that's going to be 9 times 4 over 2, 36 over 2, 18. Plugging in 0 gives us nothing, so we get 6. Voila, there we go. Again, a very long process to do this using direct method. Much, much simpler because it's a closed, counterclockwise oriented or positively oriented figure to use Green's theorem. Alright, example 2. This will be the last example on this particular video, and then we'll come back with the second video because, as you can tell, these problems can take a while, especially when you have to do both methods. So we're going to do the line integral here directly and using Green's theorem. Once again, we'll see Green's theorem is so much faster. So let's go ahead and at least look at our region. So we've got C is the triangular region with vertices at 0, 0. A vertex at the origin, 1, 0, and 1, 2, something like that. So we got our triangular region. It looks like this. It is supposed to be oriented counterclockwise. It states so because the integral indicates that with the little circle. So it's a closed, positively oriented region. We're good there. So let's go ahead and name these C1, C2, C3. C1 and C2 will not be difficult to do. C3 will involve just a little bit more, but it's really not difficult because it is linear. And since they are linear, once again, all of the line integrals are going to go from 0 to 1. So 0 is less than or equal to t, less than or equal to 1. So let's just do C1 first. So C1 is going to be defined from 0, 0 to 1, 0. So that means that x is simply going to be t. Y is going to be 0. So dx equals dt. dy equals 0. Let's see here. Fortunately, that line integral is going to be 0 because there is a y in both pieces, and we're multiplying everything by y, so we get the line integral is 0 plus 0, which is 0. So C1 was easy. Let's look at C2. C2 is the vertical line going from 1, 0 to 1, 2. So x is constantly going to be 1, which means that dx is 0. Y starts at 0 and goes up to 2, so y will be 2t. And then dy is going to be 2 dt. So in line integral for C2, the first part is 0, because it's got the multiplied by dx, which is 0. The second part is actually going to have something. So we've got x squared, which is 1, y cubed, which is going to be 8t cubed, and then, oops, that should not be a plus in between there. I apologize. Let's make that a multiplication. Dy, and then dy is 2 dt. So let's go ahead and finish this one off. So we're going to have the line integral from 0 to 1 of 16t cubed dt, which is going to be, let's see, antiderivative of that's going to be 4t to the fourth from 0 to 1, so that just gives us 4 if you plug in the 1. Excuse me. Alright, so now let's take a look at C3. And C3 will be the one that's the most involved. So C3 is going to go from the point 1, 2 to 0, 0. C3 goes from 1, 2 to 0, 0. So x starts at 1 and goes down 1. So it should be 1 minus t. Y starts at 2 and decreases by 2, so minus 2t. So dx is negative dt, and dy is negative 2 dt. So yeah, this is definitely going to give us stuff to plug in here. So our line integral for C3, let's see, what do we have first here? xy dx. So we're going to have x, y, dx is negative dt, so I'll just write that in there for now, and we'll pull that negative through later. The second part of that is x squared y cubed dy. X squared y cubed dy. Yeah, that looks right. Alright, I'm sure you can already see this is going to be a little bit of a pain, but this is what we're dealing with here. So let's go ahead and see if we can figure this thing out. Alright, so on the first one here, you know what? If we're smart about this, I see something here that might actually help us out. So hopefully you guys can notice, because otherwise this is, whoops, what happened there? This could be a real pain. Hopefully you guys see in this parentheses right here, 2 minus 2t. I can factor a 2 out of that. By the way, the line integral will go from 0 to 1. I can factor a 2 out of this. So what I'm going to get is 2, 1 minus t, 1 minus t. And I'll throw the negative out in front of that for the dt. Hopefully you can see the same general idea is going to happen over here. I'm still going to have this 1 minus t squared. But then again, I can factor the 2 out of here, which is going to give me a, in this case, I'm not actually factoring a 2, because technically it would be a 2 cubed that I'm factoring out. So I'd have to pull an 8 out. And then I'll have a 1 minus t cubed left over. And I've got negative 2 dt. Now, simplifying all that just a little bit will help. So this is going to be a negative 2, and then I've got 1 minus t squared dt. And then over here, I've got a 1 minus t squared times a 1 minus t cubed, which is going to be a 1 minus t to the 5th. And then I've got this 8 times the negative 2, so really I'm going to have a negative 16 dt. Now the reason that that's helpful is because now I can do a very quick u substitution here, and I can use it for both of these. I'm going to let u equal 1 minus t, and then du will just equal negative dt, so dt equals negative du. So let's go ahead and see what happens now when we plug this stuff back in. We can change the bounds if we want to. We don't have to. We can go back at the end. It doesn't really matter. So let's see, like I said, let's see what happens here. Let's go back to green for this. So now we're going to have an integral of negative 2u squared minus 16u to the 5th. And dt, let's go ahead and change these bounds. I think this will be easy enough to do. So dt is going to become negative du. But if I put the negative out front, it's going to flip the bounds. Yeah, I'll write this in a couple steps just to make sure everybody can see it. Let's go ahead and change the bounds. If I plug 0 in, we're going to get 1. If I plug 1 in, we're going to get 0. So hopefully you can see now why I want to get rid of that negative out in the front there and flip these bounds over. That's probably going to be the easiest thing to do. So we're going to flip the bounds and make this an integral from 0 to 1 of negative 2u squared minus 16u to the 5th du. Something else doesn't seem right there. I don't know. I'll figure it out as we go. Oh, I think I see what it was. That negative 16 is going to become positive when I take the negative from the du out, I think. Let's go ahead and check it out and find out. So we'll go from 0 to 1. Let's see, that's going to be negative 2/3 u cubed minus, what's that, 16/6? Is that 8/3 u to the 6th? Yeah, I think that's right. I'm still not sold on this minus sign. I have to rethink about this for a second here. And then we're going to evaluate that from 0 to 1. So if I plug 1 in, we'll get negative 2/3. Plugging 1 in here, we get negative 8/3. No, I think this is right. We're good. We're good. This is okay. And that's going to equal negative 10/3. Got to scroll that up a little bit there. Wow, okay. So yeah, that's a bit of a pain. That was just the 3 line integrals. So we got 0 plus 4 plus negative 10/3. So we're going to have 0 plus 4 minus 10/3, which is, well, it's 4 minus 10/3, 12/3 minus 10/3, 2/3. So that should be the line integral over c equals 2/3. Again, very long process to do all that stuff. Let's go all the way back up here, and now we're going to do Green's theorem. And again, we're going to show how short this is. So, Green's theorem, once again, integral over a closed curve of p dx plus q dy is going to be the same thing as the double integral over d of dq dx minus dp dy dA. Got a little something going on here. Get rid of that red there. Okay. All right, so let's show it. Well, my region as a type 1, trying to write with an eraser isn't going to work very well. As a type 1 region, I think still type 1 would be easiest, so we'll go dy dx. If that's the case, x goes from 0 to 1, and y has to go from a function to a function. Well, that function right there is y equals 2x. So y is going to go from 0 to 2x. So this thing right there is y equals 2x. So that'll be dy dx. Alright, so we need dq dx. Remember, q is the second one. That's q right there. So dq dx is going to be 2xy cubed. And then dp dy is the first one, so that's just going to be x. Alright, antiderivative with respect to y is going to be, what's that going to be? Let's see, y to the fourth, so we'll divide by 4. That's going to be 1/2 x y to the fourth minus xy from 0 to 2x. So plugging in a 2x first, let's see, oh boy, we're going to get 2 to the fourth is 16, so that's 16x to the fourth times x is 16x to the fifth, but dividing by half is really 8x to the fifth. Plugging in the 2x for the y, we get minus 2x squared. Plugging in 0 for all the y's, we get nothing. Good, almost done. So now if we take the antiderivative of this thing with respect to x, we're going to get 8x to the sixth over 6, which is 4/3 x to the sixth, minus 2/3 x cubed from 0 to 1. Plugging in a 1, we get 4/3 minus 2/3. Plugging in 0, we get nothing, so we get 2/3, and that matches what we had in the bottom. So much faster, so much easier. I apologize for the length of these videos, but these will get a little bit shorter as far as doing the problems is concerned as we go. There will be a proof in the next video, which will make it a little bit longer video.